In quantum field theory, the Kasmir effect and the Kasmir polar force are physical forces arising from a quantized field. They are named after the Dutch physicist Hendrik Casimir. The typical example is of two uncharged metallic plates in a vacuum, placed a few nanometers apart. In a classical description, the lack of an external field also means that there is no field between the plates, and no force would be measured between them. When this field is instead studied using the QED vacuum of quantum electrodynamics, it is seen that the plates do affect the virtual photons which constitute the field, and generate a net force, either an attraction or a repulsion depending on the specific arrangement of the two plates. Although the Kasmir effect can be expressed in terms of virtual particles interacting with the objects, it is best described and more easily calculated in terms of the zero-point energy of a quantized field in the intervening space between the objects. This force has been measured and is a striking example of an effect captured formally by second quantization. However, the treatment of boundary conditions in these calculations has led to some controversy. In fact, Kasmir's original goal was to compute the van der Waals force between polarizable molecules of the metallic plates. Thus it can be interpreted without any reference to the zero-point energy, vacuum energy, of quantum fields. Dutch physicists Hendrik B.G. Casimir and Dirk Polder at Philips Research Labs proposed the existence of a force between two polarizable atoms and between such an atom and a conducting plate in 1947, and, after a conversation with Niels Bohr, who suggested it had something to do with zero-point energy, Casimir alone formulated the theory predicting a force between neutral conducting plates in 1948. The former is called the Kasmir polar force, while the latter is the Kasmir effect in the narrow sense. Predictions of the force were later extended to finite conductivity metals and dielectrics by Lifshitz and his students, and recent calculations have considered more general geometries. It was not until 1997, however, that a direct experiment by S. Lamoureux, described above, quantitatively measured the force to within 15% of the value predicted by the theory, although previous work e.g. van Blokland and Overbeek 1978 had observed the force qualitatively, and indirect validation of the predicted Kasmir energy had been made by measuring the thickness of liquid helium films by Sobieski and Anderson in 1972. Subsequent experiments approach an accuracy of a few percent. Because the strength of the force falls off rapidly with distance, it is measurable only when the distance between the objects is extremely small. On a submicron scale, this force becomes so strong that it becomes the dominant force between uncharged conductors. In fact, at separations of 10 nm, about 100 times the typical size of an atom, the Kasmir effect produces the equivalent of about 1 atmosphere of pressure, the precise value depending on surface geometry and other factors. In modern theoretical physics, the Kasmir effect plays an important role in the Kurzbag model of the nucleon, and in applied physics, it is significant in some aspects of emerging microtechnologies and nanotechnologies. Any medium supporting oscillations has an analog of the Kasmir effect. For example, beads on a string as well as plates submerged in noisy water or gas exhibit the Kasmir force. Overview. The Kasmir effect can be understood by the idea that the presence of conducting metals and dielectrics alters the vacuum expectation value of the energy of the second quantized electromagnetic field. Since the value of this energy depends on the shapes and positions of the conductors and dielectrics, the Kasmir effect manifests itself as a force between such objects. Possible causes. The causes of the Kasmir effect are described by quantum field theory, which states that all of the various fundamental fields, such as the electromagnetic field, must be quantized at each and every point in space. In a simplified view, a field in physics may be envisioned as if space were filled with interconnected vibrating balls and springs, and the strength of the field can be visualized as the displacement of a ball from its rest position. Vibrations in this field propagate, and are governed by the appropriate wave equation for the particular field in question. The second quantization of quantum field theory requires that each such ball-spring combination be quantized, that is, that the strength of the field be quantized at each point in space. At the most basic level, the field at each point in space is a simple harmonic oscillator, and its quantization places a quantum harmonic oscillator at each point. Excitations of the field correspond to the elementary particles of particle physics. However, even the vacuum has a vastly complex structure, so all calculations of quantum field theory must be made in relation to this model of the vacuum. The vacuum has, implicitly, all of the properties that a particle may have: spin, or polarization, in the case of light, energy, and so on. On average, most of these properties cancel out. The vacuum is, after all, empty in this sense. One important exception is the vacuum energy, or the vacuum expectation value of the energy. The quantization of a simple harmonic oscillator states that the lowest possible energy or zero-point energy that such an oscillator may have is. Summing over all possible oscillators at all points in space gives an infinite quantity. To remove this infinity, one may argue that only differences in energy are physically measurable. This argument is the underpinning of the theory of renormalization. In all practical calculations, this is how the infinity is always handled. In a wider systematic sense, however, renormalization isn't a mathematically harmonious method for the removal of this infinity, and it presents a challenge in the search for a theory of everything. Currently there is no compelling explanation for why this infinity should be treated as essentially zero. A non-zero value is essentially the cosmological constant, and any large value causes trouble in cosmology. Relativistic van der Waals force. Alternatively, a 2005 paper by Robert Jaffe of MIT states that Kasmir effects can be formulated and Kasmir forces can be computed without reference to zero-point energies. They are relativistic, quantum forces between charges and currents. The Kasmir force, per unit area, between parallel plates vanishes as alpha, the fine structure constant, goes to zero, and the standard result, which appears to be independent of alpha, corresponds to the alpha infinity limit, and that the Kasmir force is simply the relativistic, retarded, van der Waals force between the metal plates. Effects. Kasmir's observation was that the second quantized quantum electromagnetic field, in the presence of bulk bodies such as metals or dielectrics, must obey the same boundary conditions that the classical electromagnetic field must obey. In particular, this affects the calculation of the vacuum energy in the presence of a conductor or dielectric. Consider, for example, the calculation of the vacuum expectation value of the electromagnetic field inside a metal cavity, such as, for example, a radar cavity or a microwave waveguide. In this case, the correct way to find the zero-point energy of the field is to sum the energies of the standing waves of the cavity. To each and every possible standing wave corresponds an energy. Say the energy of the nth standing wave is. The vacuum expectation value of the energy of the electromagnetic field in the cavity is n. With the sum running over all possible values of n enumerating the standing waves, the factor of 1/2 corresponds to the fact that the zero-point energies are being summed. It is the same 1/2 as appears in the equation. Written in this way, the sum is clearly divergent. However, it can be used to create finite expressions. In particular, one may ask how the zero-point energy depends on the shape S of the cavity. Each energy level depends on the shape, and so one should write for the energy level and for the vacuum expectation value. At this point comes an important observation: the force at point P on the wall of the cavity is equal to the change in the vacuum energy. If the shape S of the wall is perturbed a little bit, say by, at point P, that is, one has. This value is finite in many practical calculations. Attraction between the plates can be easily understood by focusing on the one-dimensional situation. Suppose that a movable conductive plate is positioned at a short distance from one of two widely separated plates, distance L apart. With A L. The states within the slot of width are highly constrained so that the energy E of any one mode is widely separated from that of the next. This is not the case in open region L, where there is a large number, about L/A, of states with energy evenly spaced between E and the next mode, in the narrow slot. In other words, all slightly larger than E now. On shortening a by DA0, the mode in the slot shrinks in wavelength, and therefore increases in energy proportional to DA/A, whereas all the outside L/A states lengthen, and correspondingly lower energy proportional to DA/L. Note the denominator. The net change is slightly negative, because all the L/A mode's energies are slightly larger than the single mode in the slot. Derivation of Kasmir effect assuming Zeta regularization. In the original calculation done by Casimir, he considered the space between a pair of conducting metal plates at distance apart. In this case, the standing waves are particularly easy to calculate, because the transverse component of the electric field and the normal component of the magnetic field must vanish on the surface of a conductor, assuming the parallel plates lie in the xy plane. The standing waves are where stands for the electric component of the electromagnetic field, and, for brevity, the polarization, and the magnetic components are ignored here. Here, and are the wave vectors in directions parallel to the plates, and is the wave vector perpendicular to the plates. Here, and is an integer resulting from the requirement that vanish on the metal plates. The frequency of this wave is where c is the speed of light. The vacuum energy is then the sum over all possible excitation modes, where A is the area of the metal plates, and a factor of 2 is introduced for the two possible polarizations of the wave. This expression is clearly infinite, and to proceed with the calculation, it is convenient to introduce a regulator, discussed in greater detail below. The regulator will serve to make the expression finite, and in the end will be removed. The Zeta-regulated version of the energy per unit area of the plate is. In the end, the limit is to be taken. Here S is just a complex number, not to be confused with the shape discussed previously. This integral/sum is finite for S real and larger than 3. The sum has a pole at S equals 3, but may be analytically continued to S equals 0, where the expression is finite. The above expression simplifies to where polar coordinates were introduced to turn the double integral into a single integral. The in front is the Jacobian, and the comes from the angular integration. The integral converges if S greater than 3, resulting in the sum diverges at S in the neighborhood of 0, but if the damping of large frequency excitations corresponding to analytic continuation of the Riemann zeta function to S equals 0 is assumed to make sense physically in some way, then one has but and so one obtains. The analytic continuation has evidently lost an additive positive infinity, somehow exactly accounting for the 0-point energy, not included above, outside the slot between the plates, but which changes upon plate movement, within a closed system. The Kasmir force per unit area for idealized, perfectly conducting plates with vacuum between them is where HBAR is the reduced Planck constant, is the speed of light, is the distance between the two plates. The force is negative, indicating that the force is attractive. By moving the two plates closer together, the energy is lowered. The presence of shows that the Kasmir force per unit area is very small, and that furthermore, the force is inherently of quantum mechanical origin. Note, in Kasmir's original derivation, a movable conductive plate is positioned at a short distance from one of two widely separated plates, distance L apart. The 0-point energy on both sides of the plate is considered. Instead of the above ad hoc analytic continuation assumption, non-convergent sums and integrals are computed using Euler-Maclaurin summation, with a regularizing function, e.g., exponential regularization, not so anomalous as in the above. More recent theory. Kasmir's analysis of idealized metal plates was generalized to arbitrary dielectric and realistic metal plates by Lifshitz and his students. Using this approach, complications of the bounding surfaces, such as the modifications to the Kasmir force due to finite conductivity, can be calculated numerically using the tabulated complex dielectric functions of the bounding materials. Lifshitz theory for two metal plates reduces to Kasmir's idealized 1/4 force law for large separations much greater than the skin depth of the metal, and conversely reduces to the 1/3 force law of the London dispersion force, with a coefficient called a Hamaker constant, for small a, with a more complicated dependence on a for intermediate separations determined by the dispersion of the materials. Lifshitz's result was subsequently generalized to arbitrary multilayer planar geometries as well as to anisotropic and magnetic materials, but for several decades the calculation of Kasmir forces for non-planar geometries remained limited to a few idealized cases admitting analytical solutions. For example, the force in the experimental sphere plate geometry was computed with an approximation, due to Derivation, that the sphere radius r is much larger than the separation a, in which case the nearby surfaces are nearly parallel, and the parallel plate result can be adapted to obtain an approximate r/3 force, neglecting both skin depth and higher order curvature effects. However, in the 2000s a number of authors developed and demonstrated a variety of numerical techniques, in many cases adapted from classical computational electromagnetics, that are capable of accurately calculating Kasmir forces for arbitrary geometries and materials, from simple finite size effects of finite plates to more complicated phenomena arising for patterned surfaces or objects of various shapes. Measurement. One of the first experimental tests was conducted by Marcus Parnay at Philips in Eindhoven, in 1958, in a delicate and difficult experiment with parallel plates, obtaining results not in contradiction with the Kasmir theory, but with large experimental errors. Some of the experimental details as well as some background information on how Kasmir, Polder, and Parnay arrived at this point are highlighted in a 2007 interview with Marcus Parnay. The Kasmir effect was measured more accurately in 1997 by Steve K. Lamoro of Los Alamos National Laboratory and by Umar Moeddine and Anushri Roy of the University of California at Riverside. In practice, rather than using two parallel plates, which would require phenomenally accurate alignment to ensure they were parallel, the experiments use one plate that is flat and another plate that is a part of a sphere with a large radius. In 2001, a group, Giacomo Bresci, Gianni Caruno, Roberto Onofrio, and Giuseppe Ruoso, at the University of Padua, Italy, finally succeeded in measuring the Kasmir force between parallel plates using micro-resonators. Regularization. In order to be able to perform calculations in the general case, it is convenient to introduce a regulator in the summations. This is an artificial device, used to make the sums finite so that they can be more easily manipulated, followed by the taking of a limit so as to remove the regulator. The heat kernel or exponentially regulated sum is where the limit is taken in the end. The divergence of the sum is typically manifested as for three-dimensional cavities. The infinite part of the sum is associated with the bulk constant C, which does not depend on the shape of the cavity. The interesting part of the sum is the finite part, which is shape-dependent. The Gaussian regulator is better suited to numerical calculations because of its superior convergence properties, but is more difficult to use in theoretical calculations. Other, suitably smooth, regulators may be used as well. The Zeta function regulator is completely unsuited for numerical calculations, but is quite useful in theoretical calculations. In particular, divergences show up as poles in the complex S-plane, with a bulk divergence at S equals 4. The sum may be analytically continued past this pole to obtain a finite part at S equals 0. Not every cavity configuration necessarily leads to a finite part, the lack of a pole at S equals 0, or shape-independent infinite parts. In this case, it should be understood that additional physics has to be taken into account. In particular, at extremely large frequencies, above the plasma frequency, metals become transparent to photons, such as X-rays, and dielectrics show a frequency-dependent cutoff as well. This frequency dependence acts as a natural regulator. There are a variety of bulk effects in solid-state physics, mathematically very similar to the Kasmir effect, where the cutoff frequency comes into explicit play to keep expressions finite. These are discussed in greater detail in Landau and Lifshitz, Theory of Continuous Media. Generalities. The Kasmir effect can also be computed using the mathematical mechanisms of functional integrals of quantum field theory, although such calculations are considerably more abstract and thus difficult to comprehend. In addition, they can be carried out only for the simplest of geometries. However, the formalism of quantum field theory makes it clear that the vacuum expectation value summations are in a certain sense summations over so-called virtual particles. More interesting is the understanding that the sums over the energies of standing waves should be formally understood as sums over the eigenvalues of a Hamiltonian. This allows atomic and molecular effects, such as the van der Waals force, to be understood as a variation on the theme of the Kasmir effect. Thus one considers the Hamiltonian of a system as a function of the arrangement of objects, such as atoms, in configuration space. The change in the zero-point energy, as a function of changes of the configuration, can be understood to result in forces acting between the objects. In the Kurbag model of the nucleon, the Kasmir energy plays an important role in showing the mass of the nucleon is independent of the bag radius. In addition, the spectral symmetry is interpreted as a non-zero vacuum expectation value of the baryon number, cancelling the topological winding number of the pion field surrounding the nucleon. Dynamical Kasmir effect. The dynamical Kasmir effect is the production of particles and energy from an accelerated moving mirror. This reaction was predicted by certain numerical solutions to quantum mechanics equations made in the 1970s. In May 2011, an announcement was made by researchers at the Chalmers University of Technology in Gothenburg, Sweden, of the detection of the dynamical Kasmir effect. In their experiment, microwave photons were generated out of the vacuum in a superconducting microwave resonator. These researchers used a modified squid to change the effective length of the resonator in time, mimicking a mirror moving at the required relativistic velocity. If confirmed, this would be the first experimental verification of the dynamical Kasmir effect. Analogies. A similar analysis can be used to explain Hawking radiation that causes the slow evaporation of black holes, although this is generally visualized as the escape of one particle from a virtual particle-antiparticle pair, the other particle having been captured by the black hole. Constructed within the framework of quantum field theory in curved spacetime, the dynamical Kasmir effect has been used to better understand acceleration radiation such as the Unruh effect. Repulsive forces. There are few instances wherein the Kasmir effect can give rise to repulsive forces between uncharged objects. Evgeny Lifshitz showed, theoretically, that in certain circumstances, most commonly involving liquids, repulsive forces can arise. This has sparked interest in applications of the Kasmir effect toward the development of levitating devices. An experimental demonstration of the Kasmir-based repulsion predicted by Lifshitz was recently carried out by Munday et al. Other scientists have also suggested the use of gain media to achieve a similar levitation effect, though this is controversial because these materials seem to violate fundamental causality constraints and the requirement of thermodynamic equilibrium, Kramer's chronic relations. Kasmir and Kasmir polar repulsion can in fact occur sufficiently anisotropic electrical bodies. For a review of the issues involved with repulsion, see Milton et al. Applications. It has been suggested that the Kasmir forces have application in nanotechnology. In particular, silicon integrated circuit technology-based micro and nano-electromechanical systems, silicon array propulsion for space drives, and so-called Kasmir oscillators. On the 4th of June, 2013, it was reported that a conglomerate of scientists from Hong Kong University of Science and Technology, University of Florida, Harvard University, Massachusetts Institute of Technology, and Oak Ridge National Laboratory have for the first time demonstrated a compact integrated silicon chip that can measure the Kasmir force.